In this panel, Vint asked us to give you a perspective on wireless and sensors. I'm Craig Partridge. I'm the moderator of the session and made the presumptuous step of being moderator and allowing myself a couple of minutes to try to set the stage, with the idea being that the following speakers could then all tell you either based on what I said, could use it as a base, or could spend their time telling you how horribly stupid I was, either of which was perfectly acceptable. I think many of you in the room know me, but for those who don't, I got into this internet. I joined BBN about 5 or 6 months after the TCP/IP cutover started, and have been lucky enough to be doing networking research ever since. Did internet email and network management research in the 80s, did high-performance networking research in the 90s, and for most of the past decade have been hanging around worrying about wireless issues in various dimensions. I still don't claim to understand wireless, however. So first of all, I just wanted to give a big picture so everybody was sort of on the same page, or at least knew what they were disagreeing with. The conventional technology wisdom for the future, and I guess this also requires explanation. I'm a futurist. I'm spending most of my time worrying about what the world's going to look like 10 or 20 years from now. If you asked me about routing table problems for next year, I wouldn't have a clue what to say, but I could tell you about them for 15 years in the future. So the conventional wisdom for the future is that we're going to see something like that circle on the right. That is, that the core of the network is going to be fiber. Some portion of the network will contain copper, sometimes all the way to the edge. So on that far side, you can see copper all the way to the edge. And for much of the edge of the network, and an ever-increasing share of the edge of the network, as well as indeed for some of our long-haul carriage, you'll use wireless. Okay. There are, at this point, so far as I can tell, no reasons to believe that this picture is incorrect. Indeed, one of the reasons that fiber is so firmly entrenched in the middle is that fiber, unlike almost any other technology available to us, creates its own spectrum very naturally. All right, we keep getting better and better at packing a fiber with far more channels. The rate of change in fiber optic termination technology is picking up, not going down. That was why when we were talking about underwater cables earlier, I was curious about what limitations they had inside the cable, because the edges of the cable are becoming more and more powerful and sophisticated every day in terms of how many channels you can pack into a fiber, how much data you can get through a particular channel, all of those sorts of wonderful things. So fiber, every time we have a fiber there, we've got an almost inexhaustible spectrum, and it's getting more inexhaustible rather than less as we go forward, which is why it will stay fixed firmly in the core. Wireless is meeting the need for us to be mobile, to be convenient, and the fact that it's a pain in the backside to wire up your facility. Indeed, nowadays, if you were buying commercial DSL, for example, what you get is a DSL circuit to your house, and then promptly they put a wireless box on the end of it. Nobody wires up their house anymore. I feel like I'm from the Stone Ages, because I wired up my house 10 years ago. So having made that general statement, let me just talk a little bit about what I see as two of the important drivers of wireless in the somewhat distant future. One is, and I apologize for the formatting problem here, this is a classic case of it going from a Macintosh to Windows and back again. Programmability. Most people I know don't seem to know this yet, but the answer is the innards of the radio, all the signs are, indeed there are such programmable radios now. The future of radios is programmable radios, okay? And in fact, the only real issue for the next 10 years is which of the two forms of programmability we're going to pick. One is what people call the software-defined radio, which is to say that you put signal processing hardware in the system. Used to say, a processor in DSPs. Now, with the rise of highly programmable, quickly programmable, field reprogrammable FPGAs, the answer is people are going heavily to FPGAs and using less DSPs, but some mix of FPGAs, DSPs, and a processor you just load your software into, and it tells the radio what to do, okay? And it will pick your frequencies, it will pick your channel capacity, it will pick your coding, it will pick the whole 9 yards, okay? There is a continuing fight, just so you know, amongst RF experts about exactly how bad the antenna problems are. I can tell you now that if you had the perfect antenna that went from, say, 1 kilohertz to several tens of gigahertz, the answer is that we have hardware all the way downstream from the antenna that could happily chop out channels at the 100 kilohertz increments and run any coding you wished on it. But the issue is getting the antenna to try to pick up that entire range. All right. So the answer is it's actually all real now. The military has radios of this type around, and they're increasingly beginning to show up in commercial radios as well. The other choice, which is a very exciting one and just gives you a sense of the range of choices, is something called the software-determined radio. Here the idea is, and this comes out partly out of the RF engineer's perspective, they say, look, there are only so many different coding schemes that make sense, There are only so many interesting ways to chop up the frequency space. So what we'll do is we'll give you an ASIC with, say, 1 million configuration variables on it. All right? And you'll just pick the right blend for your particular moment in time. Okay? But then we can make these very cheap, because these ASICs actually, to build an ASIC that's this configurable is very straightforward, and you do a large production run, and it's a whole lot cheaper than trying to pack DSPs and other things into your radio. The key distinction here is how well do you think you really understand the RF space, right? But the implications of either choice are dramatic, and the answer is that innovation in radios in the near future is going to come at the speed of a grad student's all-nighter, all right? A grad student will sit up, have an idea, will find a way to code it up in their radio, test it out, show that it works. You'll have the code. They can distribute it to others. The innovation will happen that fast. It's not clear what that will actually do for our future, because there's this whole massive policy apparatus that we have around wireless that's sort of sitting downstream of the innovation. And indeed, you'll hear some more about that later in the session. But a couple of things that it clearly could do. One is it's possible to imagine a radio, and in fact there are prototypes around that sit there, dynamically sense the spectrum, figure out which parts of the spectrum currently show no power usage and are otherwise legitimate for cannibalizing, and then use it, and exit as soon as they see somebody else trying to use that spectrum other than the people they expect, or if the incumbent shows up and actually tries to use it. All right? This would dramatically increase the amount of available wireless spectrum to people. The other thing is that it's clear that programmability blows a big hole in any business model that's based on building hardwired chips to a standard and making them and having to produce them in enough quantity to be inexpensive. So this whole notion that we care about exactly how your telephone works and choosing between CDMA and GSM and other stuff completely goes away. And the classic example I give is what will happen is that you will land in a new country, or you will walk into a new service area, and your phone will say, hi, I'm in a new service area. It will download the code to run the telephone in that service area, complete with all the right frequency assignments, and it will just work. All right? And this notion that it's somehow hardwired in your phone is a complete crock in the future. All right, so the other thing is what's going on energy. And here I'm less interested in being green than I'm interested in actually talking about how long devices are going to operate before they have to be plugged into the power grid again. All right, so this is about keeping the consumer happy. It's neat to be green too, but it turns out this is about keeping the consumer happy. So the thing to understand is that in any device such as this, we are rapidly moving towards the world in which your radio, and in particular the receive side of your radio, is eating up almost all the power. Okay? Nothing else, 10 years out from now, nothing else is going to matter except how often your radio is trying to receive data. Sending doesn't cost anywhere near as much as receiving. It does now in some technologies, but it's all headed towards receivers, or where the pain is. Okay? We can make these devices far more energy efficient than we have to date. And let me just give you a couple of data points. One is some work by a colleague of mine named Jason Reddy. I actually got to be on the paper because I contributed some teeny bit, but it's Jason's work, okay? Jason's achieved 100 times reduction in the energy consumption for the same data rate and almost exactly the same delay, okay, using a 3-state radio. All right, and what do I mean by a 3-state radio? Well, it turns out the basic way you have to save power is you have to turn the radio off. And so the problem is, when do you turn the radio on? And what Jason pioneered is a low power radio with a cattail whisker basically on it, which acts as a doorbell. And so when you wake your radio up, you only turn on enough power in the receiver so that somebody sending it full strength to you with your particular radio MAC address causes the radio to wake up. And that wakes up the high power receive radio, and you receive the data. And if you do things right, basically you can show that almost all the time you're never in high power receive mode unless somebody's actually trying to send you data, okay? And once you do that, you're pretty close to nirvana in terms of energy efficiency. It all works. It's now in its third generation and very vigorously working. When I go to Jason and talk with him about trying to make it a more widespread technology, he says, well, first of all, we might as well get the stuff we have working well, and points out that it's pretty straightforward to take the 802.11 energy-saving technologies and get about a 10x reduction in energy consumption, except nobody does it. Yeah.
What you just described, low,
yeah.
high, that's the standard definition for 802.11 power-saving mode for clients. And there are other things. I know because I wrote the spec.
Okay. Fair enough, Greg. Well, what I'm told is nobody's implementing the spec well enough that we can get it.
I did, and Atheros did. So it's not true. So what's your quantifiers? It's not true about everybody.
No, Greg, I'm not saying that you didn't do it. I know you did it. Where's the product?
No, we're not arguing. I'm just saying that you're right about 802.11. I think it's implemented in a more widespread fashion than you think, because when you get Wi-Fi certification, you have to pass the test that it's implemented. I think what happens is, like things in Windows, the standard default configuration gets shipped without the good stuff turned on.
Right. The good stuff is not turned on, and indeed some standard software won't even let you turn it on. So the answer is, when you get a box or you get an 802.11 card, your software has no idea how to drive it right. So, okay. And then what this says for our future is a couple of interesting things. One is that devices run a heck of a lot longer than they do now. The other one that gets sort of interesting and exciting is that you can imagine a certain number of devices, sensors, PDAs, and other sorts of things that actually run for a full year without recharging, which sort of gets exciting in this space. So with that, I'm now going to switch over to Larry, who can talk with you about the rich policy space and all sorts of other good things. And what we're going to do is I've told all those speakers that they get about 10 minutes. They get a question or two, such as Greg's, and then we're going to bring everybody up here to say, I said 10 minutes, right? Yeah, 10 minutes. So did I say a minute or two? We'll get 10 minutes to talk, and then we'll with a minute or so questions such as Greg's, and then we'll all come up here at the end to do a panel session. You're up.
Thanks, Craig. Again, my name is Larry Alder, and let me see if I can work this. I'm a member of what we call the Alternative Access team here at Google, which isn't that well known of a team. We're kind of a small band. We've got Rick Witt, who's in the audience, also on our team. So for those of you who don't know Google's mission, it's to organize the world's information, and sometimes people forget the last part, and make it universally accessible and useful. So I always feel that the Alternative Access team is spending a lot of time on the universally accessible part of the mission. So I always break down our mission into for the Alternative Access group, into three sub-efforts. The first, we want to see more and bigger broadband pipes. Not that Google's going to deploy them all and build them all, but we want to do what we can to help make sure there will be more and bigger broadband pipes. We want to preserve the openness of the wireline internet. I might get in trouble from Rick to saying this, but the current wireline internet's pretty open. You can buy the device you want, you can connect it to the service you want, and you can choose the application you want. That's not so much true in wireless. At least when we started this team about 2 years ago, it definitely wasn't true. The carrier selected the device for you. You got the device, the application, and the service all together. And so that's our third thing, was bringing the open ethos of the internet to wireless. And that's actually where we spent a lot of our efforts over the last couple of years. And I'm going to talk a little bit about the wireless aspects today. And in particular, I'm going to talk about spectrum. It turns out that the wireless industry is really driven by spectrum in a way that most people don't actually understand how impactful it is. The FCC makes decisions, and 15, 20 years later, those decisions manifest themselves in a whole economic ecosystem that happens. So let's talk a little bit about spectrum. So first of all, why are we concerned about spectrum? First of all, information is increasingly going wireless. I love the chart Craig put up with the fiber and the wireless. Even if every home ultimately has fiber and there's fiber everywhere, people still aren't going to plug into that fiber. Your laptop's going to be wireless, your portable thing, the last leg of it's going to be wireless. And so it's important that the spectrum is allocated to allow a lot of data to flow over that wireless. Because what we've learned at Google is that if people don't feel like they have an unlimited experience, an uncapped, unlimited experience, they constrain. and searches go down and usage goes down. They have to feel like there's unlimited capacity for them to use. So spectrum is very important. We also think it's important to have the licensed and unlicensed complements in the spectrum space. So the licensed spectrum is traditionally spectrum that's auctioned, and it's licensed to usually a carrier. This is like an AT&T, a T-Mobile, a Sprint. And the unlicensed spectrum is things that are used like Wi-Fi. You don't need any license from the government to operate. Unfortunately, there's a lot of constraints in both of them. These are constrained areas right now. It's hard to get licenses, and the unlicensed spectrum is also heavily used, so there's issues. So what are the issues? Well, the macroscopic issue is the spectrum is actually, if you look at it, from DC to daylight, as they like to say, it's not well utilized. If you wheel out a spectrum analyzer, you're going to find that most of the spectrum isn't actually active in this room. In this room, you're going to see like this little band here. I'm going to walk away. This little band here is the Wi-Fi band. You'll probably see that band very active in this room and not much else. So that means it's really wasted in frequency and in space. So like in this room might be different than outside. Outside you might see a lot of cellular signals. The other thing is that this constraint on spectrum, well, let me go to the third bullet. So we've also got a consolidation in spectrum. And this is very troubling. And I'll talk a little bit about this in a minute, the licensed spectrum has consolidated over time. In fact, if you look below 1 gigahertz right now, all the licensed spectrum essentially rests in 2 companies' hands, Verizon and AT&T. So if you believe that the industrial economy was fueled by oil and gas, you see what happens when it gets consolidated, what constraints that produced on the industrial economy. You can imagine if the information economy is driven by information bandwidth, and spectrum is going to be bandwidth, if that's consolidated in a couple companies, that's not a good thing, in my opinion. So that's one of the concerns. We have this consolidation of spectrum ownership, and that's leads us to innovation constraint. The innovation in the devices is just much slower. There's a lot of companies, individuals who would love to try all kinds of neat stuff, but they just can't because they can't get access to the spectrum. And if we look at unlicensed spectrum below 1 gigahertz, there's not really any. So here's the little spectrum map, and this gets back to kind of my main topic. I'm going to spend the most time on this. I was actually asked to talk first about LTE and WiMAX, what's happening in the industry. And my main message is the industry is actually driven by the spectrum allocation. So back in the 80s, what happened was these 2 bands of spectrum, and this is kind of drawn to linear scale. These 2 orange bands of spectrum were put out. It actually wasn't through auction. It was through a convoluted process. There's a very good book called Wireless Nation, if everyone wants to read the process the FCC went through this. But they allocated this spectrum for cellular services, and essentially AT&T and what became AT&T and Verizon were born. And wireless cell phones for cars happened in that spectrum, and outdoor applications and the big brick phones. Then in the 90s, these 2 bands were auctioned off. The PCS bands doesn't look that big in the linear scale from 0 to 3 gigahertz. And the reason I cut off at 3 gigahertz is higher than that, it's hard to do portable applications, mostly fixed. That was auctioned off, and T-Mobile and Sprint were born. And the whole small-size cell phones that you could actually use, this is where expensive car phones were. People had them. Not the masses didn't happen. When this spectrum came online, the masses got cell phones. T-Mobile and Sprint were born, and that's where we are. And today, some new spectrum, 3 bands of new spectrum have recently been allocated, and it's kind of interesting. So the first one, oh, and by the way, here's Wi-Fi I've already talked about. So the 3 bands of new spectrum is this thing called AWS, which was auctioned a couple years ago, and that's where you're seeing T-Mobile's doing the G phone. That's where the high bandwidth stuff is happening. T-Mobile's there with the AWS. And people are doing this high bandwidth 3G type of applications. Metro PCS and Leap are offering dongle service for portable broadband using that spectrum. So that is really the first spectrum where we're seeing portable broadband happening. And that's been out for a couple of years. Recently, this big 700 megahertz auction happened. And you can just see from the scale, that's a significant chunk of spectrum right there. My prediction is this is the driver for LTE. LTE is going to happen in this band. This is where mobile broadband is going to really take off in a couple of years. They'll shift some around between here and there, but this has great propagation characteristics and allows people to put out wide area coverage very effectively. The other piece of spectrum that's interesting is up here. It's the biggest block of spectrum, 2 minutes. And that's where WiMAX is happening with Clearwire. So Clearwire is being driven. They're at a disadvantage from coverage because they're way up here, but that's where WiMAX is happening. And then the final interesting thing is down here is the TV stations. And recently the FCC ruled that, well, look, there's a lot of TV channels, but in the gaps between the TV channels, we'll make that unlicensed. And we can use some of these devices that Craig talked about that are intelligent. Maybe they look at a database, and we can have some unlicensed spectrum down here. So let me wrap up my last slide really quickly. So what's going on in the industry? I already pointed out there's these significant new bands, 700 megahertz, Verizon and LTE. Verizon, AT&T will probably be doing a lot of LTE there. The TV white space will be a new land of unlicensed. The 2.5 gigahertz will be where WiMAX takes a shot here in the U.S. It could ultimately go LTE as well. And so this is what we're going to see in the market. We're going to see coming up more of these mobile broadband devices. They're going to be dongles. They're not going to be cell phones yet. They're not going to be, plug into your laptop, your cell phone. Cards, dongles, embedded. Right now, it's high prices because constrained spectrum. As that new spectrum comes along, the LTE and the WiMAX will take that mobile broadband and drive it down and make it a consumer offering. So, thanks.
Thank you. Time for a question or two if people want now, and then we'll put on Sumit. You're up next. Are we taking cross-cutting questions? Oh, I got one. Okay, go. You need a microphone. Here.
So the question I have has to do with FCC and its willingness or not to experiment with sharing of wider band channels. There was a discussion for a long time about ultra-wideband and its ability to be dynamically shared, and some of the comments that Craig made suggest it's technically possible to do that. Do you have any idea whether, from the regulatory point of view, there's any opportunity to try that out?
On the ultra-wideband, I think the story there is a little bit limited right now. And people are focusing on applications like wireless USB, things that might be also done with different variants of 802.11. I personally think the big experiment is going to go on in this TV white space, where there's this spectrum that is in between TV channels, and it's not just big blocks of spectrum everywhere. You kind of have to find your little niche, and this is going to be the first agile radio that really makes its way into the mainstream, and it's going to be done both with the sensing and with this database idea where the devices check in with a central database and the device says, I'm here in this physical location. Tell me what spectrum is available to me in this physical location. And I think a lot of the policy work is going to center around that. The ultra-wideband for now, I think, is a little bit not on the is not really being dealt with as actively by the policy people.
I've got a lot of questions. So let's take two quick ones, and then I really want to move on to the next one, and we'll do more broad cross-cutting. Okay. Tony, and we need a microphone. Denise?
In my many lives, about 8 years of it I spent in this space in the FCC, and I've actually seen similar presentations when I was there, and obviously it never happened. That's because this whole world is basically Alice in Wonderland, with all kinds of people making sure that this stuff doesn't happen. And my only comment is, I think if Google wants to see more of this happen, it has to play more effectively in the industry fora where that's going on. I used to be in, for example, CTIA, where Google was persona non grata because Google was not there. So there's a whole bunch of things you could be doing, I think, to evangelize this, and I would domestically and internationally, and I'd like to see you go for it.
Let me give just 2 seconds. So a couple of comments there. I think that's kind of the mission of the alternative access team, and we've started to dip our toe in the water. Turns out that Larry Page is a big advocate, especially of the white space, and he personally really did get involved in like this TV white space ruling, doing some personal lobbying, and I think we worked with traditional rivals like Bill Gates, and I think working together we have moved the bar a little bit on the white space, getting the ruling, And also in these auctions, we were able to get an openness provision. So Google's starting to get involved, but we have a long way to go. So your point's well taken.
There's a ton of stuff that's licensed, by the way. The characterization there is exactly right.
I have a completely different question. How's it going on the open handset front?
I'm not the best person to answer that question. Sure. I saw Chris DeBona wanted to answer, so that's perfect.
Hi. So what do you mean? No, seriously. And I'll talk about this for like a second during the session at 1:30. But we have an open handset operating system, and that runs on handsets. And some of those handsets are more open than others. Let's just say it's been crammed into the Free Runner, which is a GPS device that has a radio crammed onto it, which is open all the way to the CAD drawings and the chip specifications. And then the Android G1s are fully unlocked phones. The ADP ones are fully unlocked phones. From strictly shipping it, we have it shipping on an awful lot of handsets this year, and we've already shipped over 1 million handsets running Android. And the Android operating system itself you can manipulate heavily and then install on the dev phone. So does that answer your question? Not really.
It begins to. So microphone.
Yeah, there you go.
So are there legal limitations outside the U.S. on doing this? I don't understand the kind of the regulatory environment.
So if you look at actually modern cell phone design, what's really, really interesting about this, and we should give an extra minute or two to Sumit, and I'll take this off my talk later, is that if you look at the system on chip designs for cell phones, what you actually have on them is multiple CPUs now. You've got one arm that actually runs the operating system for the phone and one arm that runs the radio. And they're actually connected, and I'm not kidding you, using AT command set commands between them, and they share memory and that kind of thing. But it's kind of ridiculous. And in fact, the radio operating systems are often much larger than a modern cell phone operating system now, because they handle the intercompany handoff, intercountry handoff, radio power handoff requirements. I mean, it's incredibly complex software. So yes, but it's kind of they've said, we're just going to abstract away the really, really hard part about this, the regulatory, the radio power problem, and then see if that works out. And that's actually how the cell phone business has kind of been now for a while. And I think it's been very positive, actually. So.
All right. Whoops. Is this one? Okay. So.
I now want to introduce Sumit and let him get his talk in. And I do want to say this is a fun topic, and maybe we should find a way to bring it up again, either during question and answer or during another session. So.
Thanks, Craig. Good morning. My name is Sumit Agarwal, and I work on the mobile team here at Google. I don't like speaking for 10 minutes on end, so please interrupt me at any point. I'm going to tell you a little bit about the mobile team and what we do, only as an example of how we view innovation and how we're trying to bring about the future of mobile, and give you an example, actually, of how we've done a little bit of that in one particular area and how we've tried to share that innovation with the community as a whole to spur innovation and development on a much broader scale than we could have done on our own. And then I will talk just a little bit about how we might see the future going. So diving into what the two respective teams at Google do in mobile. There's the mobile team and there's the Android team. And at a very broad brush level, they operate similarly. They're looking to bring internet speed innovation in the form of services and applications out to users as quickly as possible. They then take the core enabling attributes and features that were used to take out the first reference implementation and try to share those out with the development community. And then we hope that there will be sort of a much larger wave of innovation. And so we try to do that with things like Gmail that runs in a browser using app cache and AppDB. So we're starting to use device-level aspects of the HTML5 specification to broadly distribute cheap, free applications to more users than would ever use the high-end client-based version of Gmail. Similarly, the Android team is building amazing implementations of things like Google Maps that have Street View baked right in. They were the first ones to come out with the accelerometer and compass integration in Google Maps that allow you to move the phone and have its view move in the real world along with you. And then we try to make all of that available for others to build on top of. A lot of our technology is in the Apple SDK, for example. My favorite story, though, of things emerging that we couldn't really have even predicted really comes from Google Maps for mobile. And I see Matt in the back, who works in London on our mapping team. Google Maps for mobile started way back in 2004 with a couple of guys who said, we think that these devices are going to get better and better. So sure, they're really small today and really crummy, and the bandwidth is really limited, but it's such a fundamental thing to have the ability to see maps of the real world wherever you may be. And so they plugged away on one device. They had one little client that ran on just a small number of phones, and they tried to get that out there. And Google got involved, and we started porting to more and more devices, and the phones got just a little bit better and a little bit better. And there was a long period where it was clear to everybody watching the metrics that we were below the threshold of widespread usability. It was too painful. For some people, it was too small of a screen. For others, it was too slow. For others, it was too clunky. But over time, all of those factors changed. And suddenly we saw runaway exponential growth of people using the application for what we intended them to use it for, routing and mapping and going from point A to point B, and also doing things that we hadn't really expected. We didn't think that millions of people in China, a place where we don't have roads and local information, would want to virtually explore other parts of their country. They just didn't have the opportunity to travel as much as they would otherwise have liked, and they were downloading map tiles of faraway cities in China all the time at an immense rate. And something really fascinating happened after that. We started to get signal back from all of these clients. So as we hit this critical mass of people who were using our product on cell phones all over the world, we started observing the kinds of things that we could collect. This is a single day's collection coming from Google Maps for mobile clients that are installed all over the world. It's many tens of millions of data points. We obviously record a number of parameters. I won't go into all the details, but this is the basis, and this sort of observation and evolution that really came about on its own was the genesis of our cell ID database. That was, from our point of view, a milestone in being able to take this incredibly valuable asset of geolocation information, knowing where people were at different levels of granularity, and using that in Google Maps. And so a few years after this gained some maturity, we released a feature called My Location. So in iPhone or in BlackBerry, you just tap a key and the map kind of zooms into where you are. It turns out to be an addictive and enjoyable experience for users. They tap it all day long, and they immediately run queries for things that are around them. And so the system just propagates. It creates a positive feedback cycle of more usage and more intensely local usage and greater volumes of usage. And so, of course, in keeping with that flow that I described earlier of developing an application, taking it to users, discovering core enabling infrastructure capabilities, and then sharing those with the developers, we made this available to everyone throughout the industry. And so now you've got thousands and thousands of applications that utilize this technology and benefit from this. And so that's how Google views sort of innovation in the mobile space. It's such a difficult space in which to gain access to the assets that you need, and so many of those assets have been locked down for so long that one of the most fundamental things that we're trying to bring into the industry is greater availability of these very valuable assets. By all means. Yeah, absolutely.
I'm looking at this chickenpox graph here, and I'm trying to figure out, this is not the distribution of a swine flu virus, I hope. I don't understand what it means to have a dot in the middle of the Pacific Ocean. Is this somebody asked to see the middle of the Pacific Ocean, or they were there when they asked for something? And if they were there, how the hell did they do that? I mean, what communication tool would they have used?
What about the road going across the ocean? Yeah.
As you can imagine, a huge part of what made this useful was having a sufficient amount of data to run lots of high-powered statistics, signal cleaning, noise reduction. A lot of this is just flat-out inaccuracy. Someone is driving on a highway, and we think that they're in the middle of the bay that's next to the highway. And that's okay. It doesn't matter. The system is very, very resilient.
It's not next to the bay, I'm trying to figure out. It's the goddamn Indian Ocean.
Matt, why are there data points in the middle of the Indian Ocean?
Microphone.
I think our database does get spammed as well, so a lot of this might be spam. But as Sumit said, the database is really resilient, so we have algorithms that are running continuously cleaning this up. So this probably hasn't been cleaned for spam yet.
But why is there a line? They want to know why there's that line. Do you have any idea? I don't know is my answer.
I don't know about the line.
Phones on airplanes?
There are lots of non-obvious and interesting things where some of these are noise and some of them aren't, and we just don't always know the answer. Could entirely be. There are lots of applications that are feeding data back into our system.
It's Obama's BlackBerry.
It's Obama's BlackBerry. I'll tell you one quick story, though, about resilience that I think was interesting. It was obvious to us that because we were doing this on our own, certain other entities in the space who might have access to the cell towers themselves might take a dim view of our actions, of our taking records of where all these cell towers were located. And so they said, we're going to rename these. And we said, we know. We know you're going to rename these. And said, well, we're going to go rename them next week. So they went and they started taking some limited action in renaming. And we had anticipated that renaming would happen. And we have ways of instantly not instantly, but very, very quickly using the volume of data we're getting to deal with remapping. So the system is relatively robust and can handle people actually working against it to some degree.
What kind of location forensics? I spend a lot of my time in the location forensics world. What specifications are you using, and are they proprietary, or and if they are you going to push them out some more?
And you might know the answer to this question better than I'm not sure if I fully understand your question when you ask what specifications we're using. For what?
Geospatial information tagging with other device user forensics.
I tell you what, I'm going to intervene because of the time issue. Take that offline at lunch, and then when you figure it out, let us know.
All right, let's move on. Craig, how much time do I have? Okay. We're going to skip this because I'd rather talk about the last one, but I'll take 1 second here. The most exciting thing that we're seeing is that once you have enough sensors in the device, once it's got a baseline amount of bandwidth and connectivity, and once we see what I believe are now going to be the winning basic permutation of devices, a full touch, a keyboard plus a touch, or a slider design, constraining to that sort of more limited set of things, I think is actually going to allow everyone to focus their time and energy on deeper and more meaningful innovation. We just start knocking down all the different things that people used to formerly have individual consumer electronics devices for. Obviously, Walkman and cameras are the first to go, and we'll see progression down that list. We're trying to exploit and take advantage of the eyes of a phone, the camera, the ears, its ability to listen and process voice. Mike knows this very intimately. Its skin, its ability to feel and sense and to know that it's moving in a certain direction, and its ability to have location. Those unique, almost human abilities to sense are the things that we think will drive product development in the most exciting directions. Tesla wanted to transmit energy wirelessly almost 100 years ago, and he figured out how the plasma well would work a long, long time. And this image, I have no idea whether this works, but I'm sure someone in this room knows whether this works. Does this work? I found this on Flickr. I think it should. It just captures in my imagination what mobility is all about. It's about these tiny devices that seamlessly can go with you all over the world, tapping into whatever assets are available there, whether that's the network, as Craig was talking about, whether it's the ability to recharge itself. I don't care if it's got the ability to preserve its battery for a year or just grab energy from every table at Starbucks or the cup holder in my car. I just want it to do whatever it needs to do. And to seamlessly pull down information, energy, location, et cetera, from the cloud is really what's captivating to our imaginations. I'll talk about one or two of these. There's a slew of things that we see as 2-year, 3-year applications that are super exciting. The first one is augmented reality. We're getting to the point now where if we know where you're standing and what vector you have, and we know what direction you're facing in because we have the compass, and we might know what road you're on because we've taken the street view imagery, we start to have a pretty decent idea of what you might be seeing, and then we can start pulling information down that overlays and augments what's around you. You can then interact with that information via voice or by typing or what have you. And so we're very excited about the augmented reality. The other one is just that, as you saw in the previous example, as more and more people use these applications, that usage itself becomes a very exciting, enabling asset. And you can start harvesting people's contributions, whether that's information, whether that's communication, whether that's Twitter, whether that's location information. It creates entirely new possibilities by sheer volume of cheap sensors that I think are far beyond my ability to figure out what would come next. But that's a super exciting thing that we're seeing. And so with that, I'll wrap up. Are there any questions at the end of this? I know we've already had some questions.
I think you're at your question when
Okay.
All righty. Thank you very much. It's good fun. So, Kevin, you're up.
Wireless and sensors, sort of. Okay.
So,
Your choice of implement.
do you like the colors? Yeah, this is. So this isn't really about wireless and sensors so much as some of the things that we've been up to and some of the thoughts that I think might be interesting to discuss related to network architecture and how you interface different kinds of systems together. I'm at Intel Research in Berkeley. Watch this space for this name. In the future, it may be different. So we just have a few minutes, or I guess I just have a few minutes, and these are some of the things that I've been concerned with, and Vint mentioned some, and some other things that I think represent some of the challenges we have kind of from a network architecture point of view today. And so some of these things we're looking at. We have a project called Disruption or Delay Tolerant Networking you may be familiar with, and I'll mention it really briefly. But some of the challenges that we run into today in the TCP IP type architecture includes these addressing and reattachment. And if you have both the address space problems and the limitation on address space problems that have been mentioned, but also the management of these things and where these things like addresses get utilized in the network and network management. So if you have access control lists, you have routing, you have all these sorts of things, and you have policy that's usually expressed at that granularity. This is problematic when you change provider, if you have mobility, if you have things move around. And there's a number of different pieces of work going on, some in the IETF context, some in the more theoretical context. They're trying to deal with this problem. I think personally that one of the biggest challenges is actually rooted in terms of an algorithmic type underpinning for it. There's been, in the last, I'd say 5 years or 6 years, some interesting theoretical results from routing scalability, but most of this is quite divorced from some of the work that's been going on in the standards type organizations and most of the things that I see there. So I think there's a bunch of opportunity there, and the next slide I have will be about opportunity. The next part is about disruptions in performance. So we started out, Vince started out before me and this other group worrying about networks with long propagation delay and dealing with things that are, at interplanetary type distances. My interest involved also communicating more terrestrially, but if we had models of mobile ad hoc networks and even other sorts of networks that have wireless connectivity, but they don't remain connected all the time. If you've had the experience, you probably have your phone goes out, it comes back, it goes out, and a lot of times we have an internet stack that's implemented on top in that phone or whatever that device is, and we have internet coded applications that sit on top of that stack, and by and large they've been constructed in such a way that if you lose that data connection, something kind of unfortunate happens. I also carry around a G phone. I didn't sign up for the data service. It's an interesting experience. I only get the connectivity when I have Wi-Fi nearby, and a number of the applications just kind of fall over when you have that. Not that I'm really digging at Google in particular, but it's an observation I've made. And then this last one is may startle you a little, I don't know, which is that I think packets are actually a problematic abstraction for security properties that we want to have. Now, it's not packets totally in general, but packets have the benefit of statistical multiplexing gain. Right? If you have links that you want to keep busy, it's useful to be able to merge different things called packets that are relatively small together. But when we combine packets with the type of encapsulation and protocol layering we've done, then we run into problems when we want to do security. And so this picture, it's a little bit hard to see, but it's the situation we have today. And it basically says up here at the top, I have maybe some metadata. These are headers, that kind of thing. And as I project this down through the protocol stack, I slice it and dice it in different ways. And some of the relevant information that I actually use for policy enforcement is put at the beginning of this thing that looks like a packet, because it's got to come out as packets down here. And then we route them. And we really would like to be able to route them along different paths to give us more robustness and to give us load balancing and so on. But when we do this, then we get things like, well, this piece at the beginning, what this says some missing, if we pass through various network elements that are attempting to do security policy enforcement, they don't actually have enough information to make very high-level decisions, and so they have to make low-level decisions. And so this is what we have today, where we have to take relatively high kind of intuitive security type policy about where things go and map it down into things like IP addresses and links and stuff like that. And that's the place where a lot of fragility from the system and brittleness comes in, because if you change addresses and you change topology, these things don't work so well. So there's other aspects. This is the protocol kind of aspect, and I'll come back to it in a minute, but there's also host type problems. We have this open PC architecture largely that's around the world, and it was designed as a general purpose execute anything you want machine, and it's very happy to have people give to it different kinds of things to be executed whether you wanted it to or not. And so there's a number of activities that are going on to try to secure the end host, but all the way down to the hardware level, but also to try and balance that against the openness that you still want to have in the platform. And it's kind of a, it's sort of a trade-off. Of course, these things have to do with not just wireless. So that's at the beginning I said this is sort of about wireless. It's even less about sensors, but it's at least partly about wireless. And so so those are the kind of things that I think are challenges for us. However, there's new opportunities as well. And I guess I come from the area where we're at least partly looking at these clean slate designs. So there's a number of projects around the world, partly in the US, partly in Europe and others, about looking at what do we do if we could change things, or what do we do if we could change some things. And again, as we came from a place where we're interested in connectivity that could be poor, but we're also interested in interfacing different kinds of systems together and possibly pre-existing systems. So now I will touch networks of sensors for a moment. If you have some different kind of protocol architecture and you don't want to change that system, what's often done today is you put some kind of proxy agent in between maybe the internet connected cloud and the edges that, or some other networks that have like sensor networks or whatever else they happen to be. But there's not really a consistent gateway architecture that's common across all these, and one of the consequences of what we've been up to is to sort of suggest one of those. And I want to just hit some of the things we've come across quickly. Some of these we've largely accomplished, and this one is perhaps future work, which is multiple namespaces. In a protocol architecture today, what we ordinarily do and the textbook would tell you to do is you come up with a naming scheme, or you come up with an addressing scheme, and all of the agents that participate in that network architecture abide by that. And that's a little bit problematic if you want to interact with existing networks, or you want to experiment with different kinds of scaling and different kinds of naming procedures. There are, probably you're aware, different trade-offs in the performance of, say, routing based on whether the labeling of the nodes in a graph have to do with their topological location or whether they're flat identifiers, the scaling properties, things like that. So the network architecture we've been exploring actually allows you to pick your addressing structure so that you can try different routing simultaneously at the same time. And in some cases, you can address things based on their location in the network, and in other times you can address things based on their names. This part here has to do with if you have such a capability, you want to name things, let's say flat, how would you find them in a large network? How do you do routing scalability? I have 2 minutes? Okay. Most of the internet type work has all been hierarchical decomposition, so you have parts of your network, you label nodes having to do with where they are in the topology, and you summarize. While there is some alternative structures, mostly from the theory community, there's an area called compact routing, which is kind of interesting. I don't have time to describe it, but it's something we're looking at. Storage is a first-class concept, so caching and content distribution is part of the network architecture. So as packets, or whatever they are, messages, objects, pass through a switch node, they're deposited there as long as the persistent storage that's available is sufficient to make that possible, such that when you have, let's say, queries for information or matching for those, which is now supported by the extensible addressing structure, you can pull it back from the storage that's there. And this, consequently, because you have storage in the networks, you can tolerate disruption and disconnection because you can deposit things as long as you don't have QoS requirements at applications that are interactive type requirements, which we think is a fair number of them. And then finally, object level of security is data at rest, in motion, and in use subject to strong controls and provenance. So this is about today we largely secure a channel from a host to another host via something like HTTPS or some encrypted channel. But when we deposit a data object in that channel and let it out at the other side and say put it in a filing system, usually we lose the protection at that point. If somebody else gets to that filing system a different way, they can get it out. Even if the filing system is encrypted or something like that, where maybe it's secured in some other key material than ours. So as the generator or the author of some piece of data, we have rather little control over what's done with it. Now, how to do this, how to deal with this, I think involves both securing objects, so I can put them on the wall or through the network or on the USB key or whatever else, but also some level of protected subsystem on the devices that use it, so that we can have some guarantees about how to manipulate it. I said it's similar to the digital rights management, but it's not really the same thing, because it's not that the author is necessarily sort of the adversary of the user. It's more the adversary is some other party, although we could get into that discussion. And then this last is understanding by the network. The picture I showed you before is that we currently map objects down through the protocol stack into packets, and we lose important information to be able to do controls in the network. However, if you do your protocol stack the right way, I would say that you can map these higher level use controls on data into the protocol data units that are carried, such that intermediate devices can see them. So what it said another way, the use controls I have on a data object need to be copied in all the different constituents components I send through the network, so I can do higher level controls, things like firewalls in the future model, whatever. And ultimately, it should not be the case that if I walk into a wiring closet with a bunch of different routers and I just decide to pick up a cable and hook things together, that should be a problem. Right? That ought to be a benefit, not a problem. Okay. Next is one. And I think that's it. Really. So we're looking at network architecture with storage and different addressing. This is this DTN project we have. In order to realize this and to be realistic, we need to be able to have infrastructure that we can program that goes reasonably quickly. Otherwise, it won't be taken seriously. We've used programmable devices in the network back in the olden days when it was slower, like PCs that were able to be the routers for the NSFNet project. We're approaching this again with newer PC architectures at much higher speed. And then this has to do with things like the programmable wireless devices, things like that, where we can change the network topology for our own needs. So, for example, do channel selection. We can do beam forming and things like directional antennas and so on. And I think that's about it.
All right.
That's my time?
Yep. That's
okay.
Kevin's a touch over, and I want to make sure Deborah gets her moment in before we get to questions. I think we'll go straight to Deborah.
Okay.
Deborah, you're up.
So Kevin didn't apologize, but explained that he wasn't exactly speaking on the topic that he was given. And I noticed that I was speaking sort of on the topic of every other session, applications, technology, legal, standards. So, and a bit of whiplash from one topic to the next. I think if you can sort of roll back to Sumit's talk is a natural segue. So, I'm definitely not talking about sensor networks. Don't do that anymore. So what I do with a bunch of people at the Center for Embedded Network Sensing and NSF-sponsored Science and Technology Center is work on a sort of a little bit technology up and application down, building innovative applications for scientists or healthcare providers or whatever, or people interested in citizen science, wherever we can find some sort of flexibly minded client, flexibly minded because we have a certain thing to offer them, so we want them to be able to use what we have, but to sort of co-design it. So let me tell you a little bit more concretely what I'm talking about. We did work in distributed sensing for lots of different applications, and in that process recognized how useful mobile sensing is, because you're not stuck monitoring at one point in space. Right, you're moving through an environment, and then we started looking at mobile phones as those kinds of sensors, because not only are they moving through an environment, but they're often usually attached to something of interest, namely a human being. And so let me tell you concretely about 3 example applications we've built, and then I want to touch on 2 sort of semi-technical topics that I think are interesting pulling out of them. So One of them is a class of applications that is very mundane in its use of technology. It's really just geocoded imagery, but it's coordinated geocoded imagery. It's geocoded imagery with an opinion or a case to make. So the idea is whatever is the data campaign that you want to do, you post a campaign. There is a specific app that's downloaded onto your G phone or your iPhone. And in a one-click, click the app, capture the photo, appropriate tags are brought up to tag the photo. It's geocoded. It's sent up. Actually, in our case, it's sent up via Flickr, brought out to a web page that is showing that coordinated data. So this is a live URL. You can go to it as an example. You can go to garbagewatch.com, which was our first example of our data campaign on the UCLA campus. Foodyouwaste.com could be applied in the Google cafeteria from my past visits there. It's for the kids in the dorm who have cafeteria plan, and they're trying to go through efforts to get them to take less food and put less back on the conveyor tray. So getting images of the food waste that's going back on the tray. And we actually have a new one up that's called What's Invasive. We're working with the National Park Service to let hikers look for particular invasive species so that can be identified early and eradicated while they're still can be eradicated. So most mundane technology, geocoded images, but when given some coordinated process through web coordination, you turn that very mundane into a pretty powerful advocacy and data capture technique. Second example, I actually want to move over to the right side, is an application that we call And Wellness, as sort of a play on words. Our first implementation of it is in Android, but it's also that your phone is also for wellness, just not just for communications. And the idea here is sort of a takeoff on the geocoded image, but instead of everything being about images, it's also about that notion of self-report. So in many things having to do with health monitoring, whether you're monitoring for how you're doing on a chronic disease, whether you're trying to titrate medicine, changing medication and seeing how you're doing, whether you're doing an epidemiological study, or whether you're trying to help people with some behavior change, such as how they eat, how they exercise or don't. One of the only mechanisms that we have now to do epidemiological studies, patients reporting back to physicians, et cetera, is through what's referred to as retrospective self-report. Every once in a while, you go and talk to somebody and you tell them how this particular antidepressant or whatever it is working for you, or how this shift in one medication to another is working for you as you're trying to balance side effects, natural medication. So there are still many things that can't be sensed directly by a phone. I'm intrinsically interested. I'm not what Craig said he was, looking 10 or 20 years ahead. I'm very much right now at all those phones that are out there. I'm interested in what's on them now. And so I don't have any way of sensing your actual condition, but I have very easy ways of asking you how you feel right now in the moment. Still self-report, but not retrospective, and a big difference. And I can take that self-report, and I can geocode it and timestamp it and upload it to a web server and give you back information about what you said over time. So our first instantiation of And Wellness is just a simple dietary tool, which it comes up both randomly or you can trigger it. And then we're building some adaptive stuff so it comes up not randomly, but at smart times. Asked you when you last ate, what you ate, were you on plan, was it good quality, who did you eat with? Whatever is your diet plan isn't usually what really matters. The issue is that people don't adhere to whatever the plan is. And so it comes back, and this is hard to view, a calendar view, the red being when you were off plan as opposed to when you were on plan. You look for patterns. When do I tend to mess up with my intended eating habit? Let me think about a small sustainable change I can do to address that. My colleague in psychology, who I work on this with, her favorite example is herself. If she buys strawberries on the way home, she doesn't eat ice cream at 10 p.m. Okay, reminders to buy strawberries, eat strawberries at 9 p.m. I don't eat ice cream at 10 p.m. Simple examples, but as applied to, it can be about medication adherence, it can be about physical activity adherence, and so forth. Very mundane technology. In this case, it's a geocoded response to a prompt. Final example of a type of data, and really these all combine in different ways, is what we refer to as the location trace. So this really is my GPS plus accelerometer sampled on a regular basis, every about 30 seconds in my case, which I've been doing for, before I had accelerometer on my phone, just GPS, but been doing this for over a year. So my activity trace, my location trace is sent up to a private account on a database. Activity classifiers are run over it to determine whether I'm walking, running, indoors, surface, street, highway. So now I have an activity location time series. And from that, we first, and this is another live application called PEER, which is a personal environmental impact report. Gives me back information about my inferred exposure to PM 2.5, one of the most harmful elements in air pollution. I'm not measuring PM 2.5 on my phone. I won't go into my long rant about why that's not happening anytime really soon on a massive level. But the city of, the county of Los Angeles and many other large municipalities run sophisticated air quality models. Those are a function of some number of sensors and a model that they have of microclimate and measures of weather and measures of diesel truck. And so they maintain basically rough exposure maps. They're rough, but my personal location trace gives me my personal version of what that exposure map means to me through the course of my day. So my exposure map, my personal carbon calculator, we also have a fast food exposure calculator, not whether I'm eating that food, but how much time, what are my food choices where I live? Yeah, right. Okay, so what do all these three things have in common? They're all, I think, interesting examples. There are 10 other versions of each of those things, of things you might do with location trace, coordinated geocoded images, or these kinds of ability to look at my behavior over time through geocoded prompting and then presentation. And they all have a similar architecture to them. They use existing phones, as Sumit described. I have been using a term that Vint has now almost cured me of, personal data stream. I don't know if you remember what you said the first time I mentioned that term to you. Anyway, but when we talk to the health folks, we now refer to this as sort of your living record, which is in the sense that aside from your electronic health record, there's your living record, which is what am I doing with my days? Maybe if I'm going in for regular checkups, cancer survivor, being treated for cardiovascular disease, any number of chronic diseases. 3 days before I go in, I capture my living record. I run my location trace, I capture my dietary intake, and that's part of what comes in with me when I come in for my checkup. So a common architecture that does a combination of capture, a combination of processing and curation on the web server cloud side, whatever you want to call it, as of now. It's very important that this information is kept in a historical basis. You're often looking for anomalies and for trends. And it's a combination of data that's just mine and models that exist on the web, lots of very rich GIS information. You guys know all about that. And it's this combined set of data and processing and capture that is potentially highly revealing. So one of the things that I think is interesting to talk about and that's emerging is where can we introduce points of standardization and common APIs and things like that, so all of this can happen rapidly and to people's benefit. And then the last thing I want to say before finishing is that given that I see all this happening and I see such incredible potential to what this data that's so easily captured tells us about ourselves, I see such incredible potential about what this data tells us about and other people about ourselves. And so the privacy issues are intricately tied to how easy it is to leverage the data. This isn't even like cameras on the streets of London or in the subways and the airports where computer vision is still relatively high-end processing. This stuff is easy to mine, which is why it's so exciting to look at the applications that can come out of it. So one of the things that we're looking at is sort of an architectural context in which your data, your living record, comes into a personal data vault. You own it. It is run. It might be physically distributed. It might sit in the cloud, but sit in a private container in the cloud where nobody who has any interest in it mines it in its raw form. And as you engage in services, you're doing that by sharing filtered information. Maybe in some contexts you share all of your detailed information in certain contexts, but that there is this moment of pause and this moment of indirection that allows you to keep this extremely rich historical information. And now we have a separate, very difficult problem. We've introduced a level of indirection, but still have a very hard problem of what's the right sort of a language and mechanism that lets you do sharing of the data, lets you do a kind of trace audit about where your data is going later, some of the things that Kevin was alluding to. And I'm being kicked off.
Okay, so now we ask all the panelists back up front, and people should start firing questions at us. And it looked like the first one was probably for Deborah, so I'll give her the microphone.
So, as the other participants show up, Deborah, so I was thinking about some of this information, and are you familiar with Google Flu Trends?
Google?
Flu Trends?
Yes, of course.
So, and when you were talking about some of these, environmental things that, people are looking at, Northern California, the Bay Area has a Save the Air Day kind of thing because we know we're monitoring, but the rest of the world is not monitoring. There's lots of places in the world. So a Google search on asthma symptoms that you can mine at the same time would tell people avoid this, avoid some city in Greece at that day.
Yes.
Are you looking at some of this? How do you augment it with search?
So I think it's in some sense that big generic box that I put about GIS and web, and that I see what you're describing as almost like a GIS layer that comes out of that search process, right? So you're doing that mining the data that happens through people's searches to get indications that there might be something. It's a fantastic idea to sort of think about that as a layer that I tap into through my location traces. So we haven't done that, and I hadn't had that thought until you mentioned it, until you said it. I think it's excellent. Well, I've only thought about sort of some things as being analogous to that kind of flu search. I think it's an excellent idea.
We're now 3.
You want to take this away from me so I don't talk?
No, you can talk.
No, this is for you. I'm afraid.
You want to stand up or sit down, Deborah?
I'm sorry, but they look really silly.
These chairs are quite rickety and they feel silly, okay?
Yes, go ahead.
So one dream I've had for a while, which seems like a very minor, simple application, is I'm stuck in traffic, a long line of cars in front of me, cars whizzing by, coming in the opposite direction, know everything that I want to know. Every one of them knows what I want to know. Why don't they talk to each other?
So that's starting to happen, and there's this Berkeley Millennium Project where they've capturing information off of cars. A few years ago, when I first started doing some grad seminars, doing projects, exploring this area, we did a little application where your phone with the GPS, you get the speed with which you're traversing those side streets. I looked at that, I said, oh, cool, we could do this, but I have no way of getting the right penetration out that I'm going to end up having even a minimal penetration across a city that somebody's going to have implemented it. So I implemented it so that I can get the data I need. So it's happening slowly as commercial entities are pursuing that approach. There's the capturing of the information on the surface streets, and then there's the getting it back to you. Whether in the end it really makes sense, I know it's appealing, technically appealing, to think about it coming from the cars coming back to you, but whether it really makes sense to come from the cars coming back to you or because you're checking in on a more central local repository that's getting that information, I'm not sure.
That seems to me a big architectural question, and everything that I'm seeing suggests send it back to a central repository, have it run by a service as opposed to a sort of community Manet operation. And I don't fully understand the dynamics of that. You want to say anything?
I think that as computer scientists, we'd like the answer to be the latter, but that the answer is probably the former.
It's just easier to do it that way as long as you have the connectivity probably in the other applications that are already there.
And the penetration you need. You have to assume success, and you can't work your way to success.
But you might also, though, a lot of the auto guys that are putting computers on their cars and everything are putting in networking capabilities, and they may be putting in ability to program them and put apps on there. So if that's the case and you have wireless connectivity, and you have programmable radios and all that stuff too, you could certainly do that, I think.
Could get there eventually. I just don't see it rolling out that way.
Right.
So this raises it. Oh, where we go? You had your hand up, so yes.
Yeah. So I guess you mentioned that there is a consolidation of spectrum, and as a result, and it seemed like the only solution to that problem is to use software-defined radios in order to be able to jump around the spectrum and not be constrained by the particular spectrum. And about the software-defined radios, I know Craig is very, very optimistic that in 10 years that's going to happen, but a lot of people believe that those radios are going to be very power-hungry, not agile enough, and so on, so that may or may not happen as quickly as Craig is suggesting it may happen. So if software-defined radios were not to happen, are we stuck in this consolidation of spectrum story, or there is a way out of that?
So I think you may have misinterpreted what I said. I certainly didn't try and draw the conclusion that software-defined radios were the way out and the only way out. I was saying that below 1 gigahertz, if you look at the licensed spectrum right now that's for mobile access, it's fairly consolidated. So one of the things, I agree with you, there's a lot of unanswered questions in spectrum, agile radios and spectrum sensing. I do think this database idea may help address a lot of them. I think the combination of this database and sensing could be very powerful. The idea that a device checks in with a central database to understand what's available and the parameters and the terms of that availability could really solve a lot of these power issues you talk about and so forth. I do think that the days of finding big blocks of spectrum that are open nationwide are coming to an end. You're going to find much more pockets of spectrum that are not used in space and time, and you want to take advantage of being able to use them. That's the solution, is being able to take advantage of the unused spectrum. And you got to find technologies that allow you to do that, whether it's agile radios, databases, or some other mechanisms.
So I just want to add to that, because it's clear to me that what I thought you were raising was actually a definitional problem, which is there's a third class of radio, which I didn't even discuss, which is the so-called cognitive radio, which is a radio that actually sits there, senses the spectrum, and rather than doing something predefined by the database and its location, which is very straightforward, sits there and actually computes a plan for how to use this piece of spectrum. And this gets people very excited because they start looking at things such as water filling, which, for those of you who don't know, it is the idea that that you can overlay your signal on somebody else's in certain ways to reach the full Shannon limit of the particular channel without disturbing their signal if you manage to code them orthogonally and all sorts of other charming things. The future for cognitive radios, while they're feasible, right, is much, much more distant, simply because of the computational power required to, in real time, sit down. I was on a project once that actually looked at encoding part of the FCC spectrum rules and saying, okay, when would I be allowed to operate in this space? And the answer is you can do it. And a typical laptop, this was about 5 years ago, could compute it for a small spectrum of the space in semi-real time. But the answer is, you were hauling this heavy brick of computation around with you. Whereas Larry's point about the fact that you show up in an area and you have your GPS and you download a database, and whether the database simply says these channels you can use, or here are your set of 3 or 4 options, which are the way you should behave here that should work, with maybe a tiny bit of sensing. That's the more likely style of cognitive radio we'll see in the coming years. Now, and I'm optimistic because, in fact, we now the feds are now in the process of trying to make cognitive radios for well under $1,000 per, which means that if you look at the price curve by 10 years from now, they're going to be dirt cheap.
I want to make one other, what I think is an important point. I think also that a solution to this problem of spectrum concentration is openness. So up until a few years ago, if you wanted to have a Wi-Fi in your cell phone, the carriers wouldn't let you do it. Okay? It was blocked. And the idea is they wanted to keep you on their spectrum that they could control. If the spectrum opens up, which we saw in the 700 megahertz auction, they're saying, look, any device, any application, then people can be innovative. They say, look, I'm going to use this spectrum when it's appropriate, and that other spectrum, like I'm going to move on to Wi-Fi, I'm going to move on to my femtocell. When I've got good coverage from a high bandwidth spectrum like 2.5 gigahertz, I'm going to use that. But when I have no coverage except for some low-frequency spectrum and use that. People could build devices that take advantage of the different spectrum that different people own, as long as there's open APIs and there's an open ability to do that. This idea of the one monolithic network, and we're all going to be under one monolithic network, I think those days are ending. And so I think that's also a solution to the consolidation.
Debbie, how are you doing identity management? And just a kind of a footnote, again, I love this spectrum stuff, having been in the FCC Office of Science and Technology dealing with this, the reality of who controls spectrum, and for basically for revenue earning purposes or for national security purposes is a significant factor that will bound what you do.
I can answer that, but you asked Deborah her question first.
So the easy but not adequate answer to the question of identity management. Right now, a lot of our stuff, we're just using account setup and identities that you have through other things, whether it's through Flickr or an account we set up for you on Peer. But that's not the answer, because we if you share location traces, for example, and even if you share geocoded breadcrumbs that you leave behind through images that you share, you're very easily sharing your identity, right? And so there's one aspect of just letting people know that through the breadcrumbs we leave, we share that information. But as you move into things like sharing your location, capturing your location traces and using it over time, over the course of years for some health management, and then what your insurance company or something might want from that, or how that's used, what NIH epidemiologists think about that information. They think they can anonymize data, and of course you can't, for the most part, anonymize location traces without getting rid of the information you're trying to maintain, the same problems they have with genomic data. So you can use straightforward identity management when you talk about personalized accounts, but when you go to actually use the data, which is inherently self-identifying, maybe we're going to need something like an equivalent to GINA to protect you from location discrimination in the way that you have protection from genetic discrimination. I think it's a much more complex question.
So I had a response to Tony, which was that one of the interesting things, if you go very far down this question of adaptive radios and open platforms and things, is, finding ways for people who think they own spectrum or control the spectrum to actually make money off it. And there are, in fact, straightforward ways that you can imagine that says in an open environment with a radio that you can give somebody the right to use spectrum. And most of the people who, have spectrum rights actually aren't using them in large parts of the country. And they're sitting there, and if you go to them with a proposition that says, hi, I will suddenly make that non-productive spectrum start to give you money, they get very excited. And the obvious way to think of it is that as part of the database that Larry discussed, one of the things that goes on is that there are pieces of the database which require you to have a signed credit in your device that says, hi, I'm entitled to use so-and-so spectrum. I've paid my one-year chit that says I will, I'm allowed to use, Verizon, AT&T unused spectrum in the Western United States, and you have that chit in your PDA, and so when you show up with your GPS, you can hand that shit over as part of the process of downloading the map, and you get a richer set of options about how to operate, and they're getting money because you paid them for the right for the year. And that gets them very excited, and that's sort of a way to subvert the process in which everybody feels they own it and nobody wants you on.
And the national security law enforcement guys?
You mean in terms of their spectrum, or in terms of national security law enforcement guys?
Clarify, what is it?
Yeah, what do you mean? Which particular issue are the national? They want access to which? The spectrum or the data?
Basically the signature. Who's using it for what purposes?
Right. Well, that's the open question of whether, what kind of a certificate I have to have, right? Can I just show I bought a certificate valid for a year, or does it have to have my name attached to it? And those, I'm just saying, for pragmatic purposes of trying to make sure the spectrum is available, there are mechanisms for doing that cause revenue to flow in the right ways, which may make the process a little easier. And okay.
I work in Fort Meade in cybersecurity for the Air Force, where I've been a reservist for 12 years. And although we want an enormous swath of information, the greatest chances we have of getting that information are primarily around the people who have the least sort of people who are here, people who are U.S. citizens. The people who we really, really need to get a hold of will continue to confound our ability to exert a very centralized command and control type of approach. So I'm not sure what your specific question is, but I think, yes, we want all that data. I don't think that our desire is going to match up with the reality in the near future. I'm not personally making it worse. I'm sort of trying to figure out what we should be doing. But yes, I think the situation will continue to get very, very bad for us.
One of the pieces of the puzzle here is the spectrum that's actually owned and operated by the federal government. They're the single biggest user of spectrum. A lot of it is for national security reasons, but a lot of it is given to the Department of Transportation, Department of Agriculture, and a lot of these folks just don't use it. And so one of the challenges happening in D.C. in recent years is figuring out how to create the right market incentives so they kind of use or lose their spectrum and give them the ability then to lease it out or share it with folks on an underlay basis, for example, so that there's more access freed up for commercial or other types of uses.
Yes, on that score, one of the more horrific things I discovered is that the frequency maps for the military are often set up 6 months in advance of missions. Right, that is, they sit down. There's not a whole lot of flexibility of, oh, hi, these guys need bandwidth today. It's something that they're stuck with whatever they got assigned 6 months ago when they were shipping to whatever battle area they're going into. It's spooky. But the flip side is the allocations aren't always good. There was an article recently suggesting that we don't have enough bandwidth allocated for real-time flight testing, and the reason is the more sensors on the planes, they want more bandwidth out of the planes, and they don't have a way of allocating that amount of capacity. And I looked at that and had two reactions to it, one of which is, yeah, I believe they need more capacity, but the answer is they're looking at this for like a single test. 3 months from now, they want a large amount of capacity for about 8 hours, and this is the ultimate in what you want to use dynamic spectrum for. But,
I have two questions. First one has to do with wireless as a broadcast medium. It's true that you don't have to treat radio as a broadcast medium. You can have point-to-point antennas and horn antennas and so on. But for the moment, let's imagine that we're operating in an environment where multiple parties can hear transmissions. I'm not sure that I heard very much in any of the conversations about protocols that take advantage of knowing that the various devices multiple devices may actually hear a transmission, possibly making more efficient transfers of data because multiple parties receive it. You don't have to transmit it separately, possibly other kinds of applications. So that's one piece of protocol that I'd like to hear some reactions to. The other question has to do with layering. There already were comments about the network knowing more about the applications so as to adapt better to it. Layering's been a very powerful tool because it's allowed a large number of different technologies to participate in a common structure so that it doesn't matter whether you're on a radio or an optical fiber or something else. Somehow or other you can emit an object that somebody else in the network can receive. But that's also been argued to be limiting. And so I guess I'd like to hear a little about the layering question and whether we need to break that model in order to take better advantage of either wireless or multiple transmission systems. But let me start with the first question. Kevin?
So with regards to the first one, this is other transmitters in a shared media. There's been a bunch of work at the coding layer in the last couple of years, a bunch out of MIT, that shows that kind of the convolution of multiple signals can be deconvolved in such a way that you don't have to resend things over. Where that fits in an architecture or protocol layering, I suspect would be somewhere down below. But maybe it has something more more interesting if you know ahead of time. So I don't know the exact answer, but what does routing mean in a network in which you fractionally got stuff that somebody else emitted at some previous point in time? I think the coding has been largely worked on, but I don't know if the higher layer implications on data distribution has been sort of worked out. Craig may have some things to say too, but
yeah,
okay.
Please.
So then in the cellular industry, I think things are trending away from broadcasting. So what's happening in the cellular industries is that they started with broadcast antennas, they went to sectorized antennas, And now they're really going with this OFDM that's part of WiMAX and LTE. They're going to multiple antennas that are coherently combining signals actually at the spot where the user is in order to eke as much capacity as they can out of the spectrum. So I think the trade-off they're saying is that most of their communication is not broadcast, it's unicast, and so they're starting to optimize their systems around that. Now some people like the services that Qualcomm runs that are like television to the mobile phone, that's a different thing, and they build whole different infrastructure around just a broadcast medium. But I do think cellular is trending away from broadcast and going to these more directed, spectrally efficient technologies.
So let me try to do something and channel somebody maybe we should have invited, which is Van Jacobson, who argues that the two questions you asked are the same question, and that, in fact, the broadcast aspect of wireless, when you use it right, is a wonderful tool for reaching out and finding the right person who has the right entity that has the information you are looking for locally. And he is, in fact, if you listen to his video talk that he gave here at Google, or you look at the interview that he gave in ACMQ that was published in January, he talks quite a bit about using content structures, much as Kevin described, in which you sign the data objects, okay, and then you think of moving those around. That one of the things that wireless is extremely good is finding out who has it locally, rather than the unicast model of going instead off to some server which may be off net to tell you, oh, it's over there or whatever. You say, anybody got it locally? And that, wireless, suddenly that query, which had previously been, as he puts it, a case of you sending to 10,000 people, 9,099 of whom throw it away, becomes a useful way of querying all 10,000 in the room immediately and saying who has it. And he points out in many cases you do have it. Oh boy, now we've set off both Steve and Greg, so this is fun.
Would you reconcile the answer you just gave to what Deborah gave me when I asked a comparable question with respect to peer-to-peer versus centralized sharing information?
I don't know that how much I agree or fully understand the depth of the Craig channeling Van comment, but they're different in the sense that one of my arguments for you is that you have to have this collaborative network of man-aid deployed to get all that data back to you with enough probability that you're going to count on it being useful to you. Whereas in this context, you're talking about, I think, largely communicating with things that are, for the time being, static and might well have information cached near you. So he's just, I think, talking about basic locality.
Yes.
And it's not as many sort of multi-hop. The whole system that has to come together to make it work is more involved in the man-aid case. It might ultimately go there because that would be the more optimal case once it's wildly successful. I just don't see that as the deployment path that it ends up getting on.
So the other question you asked was about the layering, and so I'm not against layering per se, but we also normally have layering with an encapsulation model, where the encapsulation model causes us to have complete opaqueness to the layer above. We just say we're not allowed to look in there. I think that's actually part of the problem, is that when you project downward, you don't do full opaque encapsulation. You still may have layering, but not this opaqueness, because it's those high-level properties that you don't want to lose. Regarding the other thing, it's true in local wireless type. This is very helpful to find things and do limited distance discovery. When you start to go further and further and further, and everybody's trying to do that, and now you're advocating going down to an object level of, say, data, or you could even push it all the way down into a word in a document. What's the scalability of that, and how do you summarize that, and how do you do that? And so the question I raised about, I think, how to do scalable discovery / routing is a really fundamental one, and that I think there's this disconnect between what we might call the networking heads and the graph theory people. And I think the graph theory people actually have something to offer, and we have something to receive, but we're speaking a different sort of language.
It could well be, and let me just say, Van argues that what the content stuff plus the ease of using broadcast media is that the narrow waist should be moved up. And so if you read Van's discussion in January, what he's arguing is that they're still layering, but the narrow waist is not IP, but it's actually right up at around content. And Greg has been waiting very patiently, which is unlike him. So,
well, is this thing on? Yeah. So the The second word that comes up when I hear the first word broadcast is storm, broadcast storm, right? So the concept is clean and easy, and it was a fallback to avoid figuring out how to deal with the inability of broadcast to scale, especially when after the broadcast there are responses, right? It just falls apart. So even though the concept is correct and you want to be able to query large numbers of people, it requires some serious engineering and maybe thought in order to make it work at scale. That's the only comment.
Which I think is probably an excellent comment on which to end and head for lunch. So I hope you all enjoyed the panel.